All right, so we're going to start with looking at chemical formulas and composition. We'll start with looking back at molar mass and some of the calculations you can do with molar mass. So let's take C4H10 and we want to calculate its molar mass. And if you remember, the way that you do that is you take the number of atoms of the first element, right? My pen's not working. Here we go. The number of atoms of the first element here, and then you multiply times its atomic mass, and then you do the same thing for the second element and the third element and the fourth element and so on. So a simple example, C4H10, but I'll take a close look at significant figures when we do this. So I have 4 times 12.011, that's from the periodic table. Maybe a more precise one that you're using, but it's a molar mass or atomic mass of carbon. And so I get 48.08044, and then I take 10 times the mass of hydrogen, and so that's 10 times 1.00794. That gives me 10.0794. Now, significant figures, I have 5 in this first number, so that's the last significant digit. And then in this second number, I end up having 6. Now, when you're adding these two numbers together, since this ends in the thousands place, this number will end in the thousands place. So if you were to round and represent that number in terms of atomic mass units, it would simply be 58.123 atomic mass units. And again, if you remember, 58.123 atomic mass units is the same as 58.123 grams per mole. Okay, so again, the molar mass can be used in a number of different ways. One, it can be used to convert grams into moles, and in order to do that, for example, you take 58.123 grams at the bottom, put 1 mole at the top. The units will cancel, and you'll end up with units of moles. Or if you want to go from moles to grams, then you have to put the moles on the bottom, and you have to put the grams at the top. And then that would be the 58.123, like that. Now, technically, since I have the unrounded number, I should use that and just keep track of the sig figs doing there. So down here, same thing, 1, 2, 3, 4 grams for every mole. The grams will still cancel, but now I'm carrying 5 significant figures in my number and an extra one just so I don't have any rounding errors in my calculations. Now, if you remember Avogadro's number is the number of atoms in a mole, or molecules in the mole. So it's 6.022 times 10 to the 23rd atoms, for example, per mole of atoms. And it can also be used as a conversion factor. So if you're given atoms and you want moles, then the atoms has to be on the bottom. And the top part has to be moles. The atoms, right, that's the 6.022 times 10 to the 23rd. I'm just going to abbreviate it so I don't have to write it. That's Na, Avogadro's number. And then the atoms will cancel. And then if I'm going from moles to atoms, I would be putting 6.022 times 10 to the 23rd atoms at the top and moles at the bottom. And rather than write it again, that Na represents the 6.022 times 10 to the 23rd. All right, so let's look at an example real quick. It says calculate the moles in molecules of C4H10 in 10 grams of C4H10. Oh, sorry, I gave the molar mass as 58.1234, and this is the last significant figure here, the digit. I'll keep the 4 for the calculations, so I only have 5 significant figures here. So when I do my calculation, I'm going to end up with 0.17204. I have 4 significant figures here. The grams, remember we're canceling grams, this becomes 0.172, and then I'm rounding to this place here because of 4 significant figures. So 0.1720 moles. Now, if I wanted to go to atoms or molecules, in this case we're looking at molecules, I'll still start with my 10 grams. I could also use this intermediate number, but if you were not asked to do this middle step, let's say you're just asked to do the number of molecules, then you would do 10 divided by 58.1234 grams. Again, 3 significant figures in that number. And then there's an Avogadro's number worth of molecules in 1 mole of those molecules. And so then this will cancel, and I'll do the calculation. And I'll end up with this as my answer, again with 4 significant figures. So this becomes 1.036 times 10 to the 23rd, and then C4H10s, like that. Okay, so another thing that you need to be familiar with in this section is how to calculate a percent composition by mass. And in order to do that, it's like any other percent, it's the part over the whole. So if you wanted to know, for example, the mass percent of hydrogen in water, right? What you'd have to do is you'd have to say, well, H2O's formula, right? There's 2 hydrogens and an oxygen, right? So using your book's periodic table, it would be calculated, for example, as 2 times 1.008 atomic mass units plus 16.00 atomic mass units, for example. And that will end up being 18.016 atomic mass units. So if you take that as your molar mass, and it's really only good to about here because of the hundredths place here, and divide it into the mass of the hydrogen, then what you would get, because this would be, for example, 2.016 atomic mass units, the mass percent of hydrogen is 2.016 atomic mass units. That's the part divided by the whole, which is the mass of the molecule, times 100, because that's how you always calculate percent. So when you do that, that ends up being 11.19%. And then rounding, to sig figs. So that's actually what this little calculation is here. If you wanted to calculate the percent carbon in CO2, you would take, for example, the mass of carbon, right, plus the mass of 2 oxygens. So that ends up being 12.011 plus atomic mass units plus 2 times and then 16.00. So that ends up being, rounded at least, 44.01. The mass of carbon is 12.011, so the percent of carbon in the compound by mass is 12.011 divided by 44.01 times 100, and you end up getting 27.289 atomic mass units, percent of carbon and CO2. So mass percent has a lot of different uses. I wanted to show you one, though, that we'll be applying at the end of the chapter towards a more complicated problem. But mass percent literally means grams per 100 grams. So let's say you had 35.34 grams of water and you wanted to know the mass of hydrogen, right? So we would write grams of hydrogen. And then we know we have 35.34 grams of water, so I'll write the formula out. And then I want to convert that into grams of hydrogen. Now, there's different approaches to this. One is to convert it into moles, and then moles of hydrogen atoms, and then mass of hydrogen atoms. But if you already have the mass percent, and by the way, that's a technique we'll cover later. What you can do is just say this. I have 11.19 grams of hydrogen for every 100 grams of H2O. And that's the definition of a mass percent. It actually doesn't matter what the units of the mass of the water are in, because it's always 100 It's parts per 100 parts, so it's 100 grams or 100 kilograms for every 100 kilograms, right? Or, sorry, gram, let's say that again. It would be like 11.19 kilograms of hydrogen for every 100 kilograms. As long as the units are the same top or bottom, you can use mass percent. So if I do this calculation, and then I'll pull this out just so you can see it, 35.34 times 11.19 divided by 100, and that comes out to be 3.95 grams. Double check that number. 3.9545 grams. Now we have four significant figures here, so that would be 3.955 grams of hydrogen. So why don't you go ahead and try to calculate the percent carbon, or sorry, the mass of carbon and 16.54 grams of carbon dioxide. Make sure when you do it, you write all the units out and use dimensional analysis so you know that you're canceling out the right things. And go ahead and pause. And so there's the solution, 16.54 grams of CO2 times 27.289 grams of carbon for every 100 grams of carbon dioxide. And then that's four significant figures because of the 16.54. And then so you round to the 3, and it's 3.6, so it becomes a 4. And so this is the answer. Just like that's the answer. There's a decimal missing here. All right.